Hi, this is a short video on our paper titled Explanation-Based Fine-Tuning Makes Models More Robust to Spurious Cues. In this paper, we attempt to answer the question, do explanations make models more robust to spurious cues? To set the scene, let's say you're trying to build a toxicity classifier for tweets to tag them as either safe or toxic. During data collection, however, you run into an issue. The issue is this. In your dataset, you have tweets with @ tags and tweets without @ tags. Due to a quirk in sampling, tweets with @ tags now tend to be more toxic compared to tweets without these tags. This presents a potential problem. We know as humans that the presence of a tag in a tweet does not cause it to become toxic. But in our dataset, the presence of a tag and the toxicity of a tweet are correlated. This can cause the model to rely on the tag to make predictions rather than more relevant factors such as the actual content of the tweet. This is the problem that we want to avoid. This problem happens because from the perspective of a model, a good feature and a spurious feature are indistinguishable. We note that a cue is spurious if it does not have any causal relationship with the label we're trying to predict. Thus, to solve the problem, we need to have some way of giving the model information about which features actually cause the label. So how do we do this? Through natural language explanations. Explanations are often useful because they indicate which features are relevant in a prediction and how they are relevant. In other words, explanations contain information about causality that we can use to mitigate spurious cues. The method we use for incorporating explanations is quite straightforward. We fine-tune large language models to output an explanation before every answer. Going through some of the benefits of our approach, we first note that it is a data-based method. Thus, it does not depend on architecture and can be easily implemented across various model families. Next, it is feature agnostic, meaning that we do not need to know about which spurious cues exist in the dataset ahead of time in order to mitigate them. Finally, our analysis shows that our method works even if explanations in the training data are generated by an LLM. Moving on to the experiments in the paper, we look at 4 different spurious cues: the length of a sentence, the presence of a word in the present tense, the presence of a plural noun, and a more subtle cue based on the sentence birth embedding of the text. To create what we call a skewed training set exhibiting spurious cues, we filter the original, unskewed training set to make spurious features perfectly correlated with the label we want to predict. We examined 4 binary classification datasets with human written explanations: Creek, ESNLI, ComV, and SBIC, and we test our method on 4 generative LMs of various families and sizes. To evaluate how much a model is affected by the presence of spurious cues in the training set, we measure 2 things. First is the accuracy drop between the model's performance on the unskewed test set when fine-tuned on a skewed training set versus an unskewed training set. The larger the drop in accuracy, the more the model was harmed by the spurious cue. Second, we also look at the correlation between the presence of a spurious cue and the model predictions on the test set. A higher correlation between the two indicates that the model is relying heavily on the spurious cue to make predictions. Now looking at our results for GPT-3 Da Vinci, on the left we see a plot measuring the average accuracy drop on all tasks, while on the right we see the prediction feature correlations. First, from the accuracy plot, we see that our method outperforms standard fine-tuning, or fine-tuning without an explanation, across all of our tasks. This outperformance is substantial. We are able to cut the accuracy drop by at least half on 3 out of 4 of the tasks that we have. We also see similar trends in the correlation plot, where we can verify that the reliance on spurious cues is heavily reduced for most datasets under explanation fine-tuning. Overall, we can say from these plots that explanation-based fine-tuning does a great job protecting models from the distributional shift after training on a dataset containing spurious cues. We also perform scaling experiments on explanation-based fine-tuning by using this method on the 4 available sizes of the base GPT-3 model. Looking at the accuracy and prediction feature correlation plots, we see that our method works better as we increase the model size. This is likely due to the fact that larger models are more capable of generating natural language explanations, similar to what we see with chain of thought prompting. Moving on to the analysis, we investigate what happens if we change the strength of the spurious cue. We find that explanation fine-tuning outperforms standard fine-tuning in cases where the spurious cues are relatively strong. This demonstrates a potential trade-off between in-distribution accuracy and out-of-distribution accuracy under explanation-based fine-tuning. Finally, we note that explanation-based fine-tuning works even if the explanations in the fine-tuning training set are written by LLMs. In summary, we demonstrate that explanations can improve model robustness to spurious cues across multiple model families and sizes. We also show that explanation-based fine-tuning works better for larger models and under stronger spurious correlations. The method also still works with model-generated explanations, making it more applicable to a wider range of datasets. All in all, to answer our original research question, we are able to show that explanation-based fine-tuning is a simple but effective way to reduce model reliance on spurious cues in large language models. Thank you so much for watching our presentation. On the left, you can see our paper on arXiv, and on the right, you can see a link to our GitHub. Thank you.